Okay, folks, we're looking at Chapter 19, which is just going to update some of the stuff that we've been covering about amines in general, and more importantly, adding some reactions to our heterocyclic aromatic compounds. So we're just going to see how that modifies some of the stuff. But a lot of this chapter is review of previous ideas, so a lot of our reactions are. All right, so first of all, nomenclature is something on amines that we've looked at. Typically what we're going to see on a basic regular old amine is we're going to actually make the longest chain part of the backbone. So the longest on this particular one, that second one, is butyamine, and we'll just make the ethyl group a substituent to it. And we typically do that all the way along. That's our blue names. And same with if we have a nitrogen as part of a ring, and we just use the aza prefix in front of cyclopropane. Now that does, if you don't remember, does define the number 1 location on all these, and that really only applies to that particular one because that's the only one with a substituent off the ring. And still, if we have coming off of the nitrogen, it's going to have an N in front of it. So like on this, 1, 2, 3, so we'd have a 3-methyl, and then IUPAC would be azacyclobutane, but technically this is also acceptable as IUPAC, so this could also be 3-methyl AZET IDINE. Okay. Other heterocycles that we've seen are having oxygen and sulfur in there. We're going to see that these have similar effects to our reactions, just ever so slight changes. And also on these, the red names are actually mostly considered IUPAC, are acceptable. Tetrahydro doesn't mean that there's 4 hydrogens, because there's technically 4 already. There's actually 8. Where there comes the tetra comes from the fact that furan, which is also a 5-member ring with oxygen, that is aromatic. And tetra just adds 4 more hydrogens to that. Alright, since we're talking about amines, we're going to refresh our memory on the pKa's of amine. And typically we see a high, very high pKa for amines in the 40s range. And if we protonate it, it does indeed drop down. At this point, we're not really expecting anything that's terribly different about that, but we will see aromatic compounds change it ever so slightly. If I don't have any pi bonds, it really doesn't matter what I do to the nitrogen. If I protonate it, I have almost the exact same pKa, within reason. These are very, very close together, even though those structures are kind of different. On to our reactions then. So our main reactions, the 2 main ways we used amines in the past are as bases or as nucleophiles. Or at least that was the 2 ways that it was introduced as. And technically speaking, the product on either one of these is still an amine. So that is fitting into this chapter quite well. Now, we didn't see too many times where we got rid of an amine, and that was mainly because the nitrogen compound, was too difficult of a leaving group. So we could actually turn almost anything other functional group into an amine, but it was very challenging to turn amine into something else because it was a poor leaving group. But we had strategies to take care of that, but just want to recall that right now. Now, that does pay off tremendously right now because amines were wonderful nucleophiles. Reason we're bringing this back into this chapter is no matter what we did, we started with amine and we made an amine. If we started with just NH3, we still made an amine. Alright, so it was very common to do that. And these were just 2 typical places where we used amines. That is definitely a review type setup. And we could also use amines to make N-amines and imines. We made imines using primary amines. And secondary amines gave us the N-amines. And of course, we use these as nice little intermediates to actually help react with the alpha position in most cases, or to turn that, at least to refer that as a nucleophile. All right. More recently, we use the nucleophilic nature of our amines to actually do some attacks to conjugated carbonyl compounds, and also to turn amines into diazonium salts and then replace them on nucleophiles with on our benzenes. And back in chapter 9, we first saw a easy way to synthesize an amine, and even though we knew NHs were terrible leaving groups, they were great nucleophiles, so we could make amines quite easily just with a standard old substitution. And also in chapter 9, we could make them with the azides, which were the nitrogen compounds, and those would go on as nucleophiles. Then when we treat them with hydrogen, with palladium, poison with carbon, we lost nitrogen gas but made an amine. Chapter 16 and 17, we saw a lot of ways we can reduce nitriles and amides into amines. That's what we got in the first two. And then we also could have done that with our enamines and imines. So what we saw a couple slides ago, if we treated that with sodium borohydride with the CN on it, we could turn those back into amines. And Gabriel synthesis was yet another way to make an amine. Had a lot of versatility with this, a lot of good yields, but it needed a primary alkyl halide, and you turn that into a primary amine. We also reduced nitro groups to make amines with the poison palladium and hydrogen, and this is one that was actually in our textbook but not actually mentioned too well, and it was another way to do a nitrile into an amine, but it used a little bit less violent conditions. The poison palladium with hydrogen might have to be at high temperature. This didn't need to be nearly as high temperature and gave excellent yields. And also, technically from previous chapter, but in the problems, was this Mannix reaction, which actually combined a formaldehyde with an amine to actually help make a alpha substitution onto a ketone. All right, and previously we saw that we can eliminate or do elimination reactions with amines. Where this comes in that was kind of interesting, the amine itself was the leaving group. So we actually created this little compound, and then when we actually took this coordinated ammonium compound and heated it up, we created an alkene. Now, when we first introduced this, it was because we were making this alkene, which was the important part back then. But technically, the other product was an amine. We didn't actually do much with it, and you don't have a lot of versatility here because the amine is typically the simplest compound that comes off. But it was a way of making amine, and that was from back in our Chapter 11 Hoffman elimination. And we also had cope elimination introduced about the same time, with just under milder conditions, and gave a similar product where we actually made an alkene, but the amine now had an OH on it, so it's a hydroxylamine. Okay, on to something kind of new. Now, new, not necessarily yet, because we want to remind ourselves beforehand what aromatic properties are. And these three guys here could be considered aromatic because we have our ring, we have continuous p orbitals, potentially, because these lone pairs could be in a p orbital, and definitely the pi bonds are, and it could be flat. So to make it aromatic, we just need that odd number of electron pairs, and we have 1, 2, 3 there, 1, 2, 3, 1, 2, 3. So as long as the pair is inside the ring, they're all aromatic. All right, now these are going to do electrophilic aromatic substitution and nucleophilic aromatic substitution. And that's the new stuff to this chapter, is how that's going to happen. So first thing, we want to talk about whether or not, and this is a review, whether or not the lone pair that's on a nitrogen is going to contribute to the electrons in the ring, or they're going to be owned totally by the nitrogen. Now, we see a drastic effect on that. So when the electrons are totally owned by the nitrogen is going to have a pKa in the 40s. It's going to be very basic, and it's going to be very much like a regular old amine. And we have that here on this pyroladine. Those lone electrons are owned only by the nitrogen. It makes it very nucleophilic at that site and very basic. But on pyrrole, the better place to put those electrons are in the ring, because it would make that ring aromatic. Thus, those lone pairs are not the nitrogens alone. They help make the ring nucleophilic, and we get drastically different properties and even reactions. And this one's not nearly as basic. Okay, we can look at the two things that are going to be happening from the electrons that are drastically going to affect physical properties. And the big difference is the electrons being pulled into the ring are creating a more nucleophilic ring. And that really affects the chemical reactivity of pyrrole, but it also affects the boiling point and melting point, because the dipole moment is then going towards that big, huge red density. On pyroladine, where it's just a nitrogen in a 5-member ring, all the electron density is located directly on the nitrogen itself. Dipole moment's going in the complete opposite direction. So totally different properties just based on that aromatic property, aromatic ring. All right, now that delocalized energy does relate to that lone pair and how centralized they are. And to compare them to just a benzene, benzene's going to have that very even distribution. Having the heteroatom is going to actually pull the electrons towards that more electronegative species, but it's not going to take it totally away. So we're going to delocalize it. It's not going to be distributed so evenly. It's going to be pulled more to that heteroatom. So it is going to actually make that a reaction center, but it's not going to totally override everything. And what I mean by not totally overriding everything, these will still do electrophilic aromatic substitution. All of them on that page. Doesn't matter if it's sulfur, nitrogen, or oxygen, they will all do it. Now, we're seeing here no Lewis acid listed, and that's actually the case. These guys are actually a little bit more reactive. That electron density, while it's not delocalized, is making that ring more nucleophilic. So these are acting, the heteroatoms are kind of acting like activators on these 5-membered rings. So we do get much easier substitutions. But if you notice, got these both in this 2 position. So nitrogen or the oxygen is number 1, and they're both going to that next adjacent spot. Now, we don't necessarily say ortho, meta, or pair anymore because these are heteroatoms. So we are going to number them by, we're going to use numbers to indicate their location. But that is how we're going to actually see that. And we will see that this happens mostly at the 2 position. Now, the main reason that happens is we can actually see that if we look at our ring itself. So what I mean by that, we're going to look at that transition state occurs if I put that Y in the 2 position. So at first, I still have both those. This Y transfers that positive up there, and this is still a double bond. Well, we can move this here. And so we're going to have equilibrium with another 5-member ring. Still a Y and an H. But now the double bond's here, and there's a positive. And one more thing that can happen, that nitrogen has definitely got a lone pair on it. It can move right there, giving us yet another version of this, where double bond, but this is now slightly positive, because it already had that H on it. So the nitrogen actually can absorb that positive. So we have 3 different ways we can arrange that. Yet if we do the 3 position, we won't have that same feature. At least I assume we don't. I'll put a Y here and an H there. Double bond was here, so this becomes positive. Yeah, because look at this. The only thing I can do is move those in here. So I can put the positive onto the nitrogen, but I don't get another way of arranging this. So I only have 2 resonance contributors. I just put that in the wrong spot. This would be double, that would be double, and the positives on the hydrogen, on the nitrogen. Yeah. And so because I get the 3 contributors to the 2 position, we're going to see only that. However, unlike a standard electrophilic aromatic substitution, since this is relatively stable by comparison, I probably will see the 3 position. And matter of fact, I do. If both the 2 positions get filled, then we will be able to add to that 3 position relatively easy. Okay, now, yeah, this was just summarizing that reactivity, and the pyrrole is actually the most active of these, so it would react the fastest. But it's not like we really need to actually see this ranking per se, because it's not like we're going to have pyrrole and furan competing with each other. They would definitely be the only reagent. Just want you to see that they are more reactive than benzene, so they are more the heteroatom in this case is a better activator. Okay, Friedel-Crafts will work on these. Matter of fact, because the heteroatom actually is a better activator, we don't need nearly as strong of a Lewis acid. Like for sulfur, tin chloride is used. It's a much more milder Lewis acid, and we still get the same type of product. Now we'll go to the 2 position, so it's acting like that same thing applies. The 2 position's more reactive. And with oxygen, our derivative is BF3THF, so that BF3 stuff is used as a Lewis acid. And pyrrole is so reactive it doesn't even need a Lewis acid. It's very strongly activated, so we can do that with no problem. But standard Friedel-Crafts here. All right, now here is something interesting. Now it's unique to that pyrrole, and it has a lot to do with the fact that the typical amine, the lone electrons are where the H goes. But on pyrrole, if I were to take that away, we lose that aromatic property. What we see happens instead, we do lose the aromatic property, but it's actually easier to attach that H to that 2 position. The 2 position is a little bit easier to protonate. Now it does, when it does attack and attach, this does, well, this one moves up here, that moves there, and the positive does go to the nitrogen. But the nitrogen does hold the positive, we just don't actually directly protonate the nitrogen, protonate the 2 position. All right, this leads to a storage issue. Turns out pyrrole is not a good substance to store for any length of time, because if it gets exposed to too strong of an acid and starts that process of protonating it, they will actually attack each other, and it makes a polymer. Now, this actually happened here at our school. Our school, we had a sample of pyrrole that was actually just a jar of plastic, I guess you could say, because it actually had gotten exposed to some acid and had just actually polymerized inside the container. What was weird for ours is it had done it and built up pressure in that container. So when we opened it, it blew a little bit of that remaining pyrrole out, and that kind of polymerized all over the fume hood as it blew out. So we had a, it looked like splatter, but it was like splattered plastic is what it kind of looked like. It was easy to clean up because it just kind of flaked off, but it was kind of weird. All right. Now, something we see that is affected by that protonation is the pKa is drastically changed. Most amines, we have a pKa around 30. Pyrrole, because that lone pair is definitely owned by the ring, is a heck of a lot harder to rip that H off. So that H is being held on to a lot tighter, raising that pKa up quite a bit. Reverse what I just said. It's holding on to the electrons between the N and the H a lot tighter, which makes it a little bit easier to transition to that negative and kick off the hydrogen. That's a better way to phrase that. Okay, and we see that along a whole slew of things. So these pKa values, we can make a call based on how well the electrons are owned. And there's that pKa for the unsaturated or saturated ring with a nitrogen, it's much more like a pKa of an amine. But as soon as we conjugate it and take away the ownership of those electrons and pull the other electrons in, we weaken that bond or weaken the attachment of the hydrogen, and we significantly lower the pKa. And that's what's happening in all these. The more heterocycles we do, the more protons we add, we shift it even more and more acidic. All right, biggest reason we see that, and the biggest reason we have difference in their properties, is where those electrons are being shared. Now, pyridine, for instance, it's a 6-membered ring with a nitrogen. Has totally different properties than pyrrole. Pyrrole was the 5-membered ring, and pyrrole we just saw was kind of an activator. And it is because its lone pairs make up the nucleophilic ring itself, help make that ring more nucleophilic. Well, this doesn't actually do that. That lone pair is actually going to have to stay outside the ring because it's already got a pi bond making up that double bond. And that makes these behave a little bit more like a standard amine. Now, they're still tremendously shielded from that nucleophilic ring, but this ring is not strongly activated. Now, we still see the same effect with the pKa, the fact that electrons are available and can be protonated. We do see that the pKa is elevated quite a bit compared to a standard old amine, but it's not elevated a huge amount. We're getting a little bit closer to standard amine range because it is almost like a lone pair owned totally by the nitrogen. All right, but we get similar reactions with that lone pair. Even though it's held on tighter than an amine and makes it a little bit less reactive, we can still do most tertiary or most reactions where we're taking advantage of the lone pairs on the nitrogen. And so we can actually do something like this and make a quaternary amine. The ring itself, the aromatic nature, won't stop that. We can also see that aromatic substitution is actually going to be very predictable where it's going on. Now, what I mean by that, this is almost acting like a deactivator. And if I put it in like the 2 or the 4 position, I end up putting a positive charge on a nitrogen that is already got just a lone pair on it. Now, normally we don't mind putting a positive charge on the nitrogen, but you will see that the only time we can easily do that is if the nitrogen's got 4 things it's bonded to. And since this only has 2, and then the other 2 electrons are making up that lone pair, makes that very unstable. But we only see that if we try to attack the 2 and the 4 position. So, what that kind of summarizes as, this has deactivated the ring, and it puts it in the 3 position. Now, if it was a benzene, we'd say this was a metadirector, but we don't use that term on heterocycles. But the 3 position is the same location as meta, and that's what we're seeing. All right. Now, that deactivated ring is not as deactivated as having 2 nitro groups on a benzene, but it is at least as deactivated as having a single nitro group. So that's going to drastically affect our electrophilic aromatic substitution. You can't do Friedel-Crafts with these because it's too deactivated. And most of the other things we can do, we actually have to step up the temperature a little bit or add a little bit stronger conditions. So like the iron bromide with bromine, you have to warm it up. And sulfuric acid, we actually have to warm it up. And ironically, it's OH in there now. And same with HNO3 and H2SO4, you will have to treat it again with some OH when you're all done. But you have to put some temperature in these, and you do notice these are all in the 3 position. That's about the only place we can put something on there. All right, but if you remember back in our benzenes chapter, if you have a deactivated ring, this should do nucleophilic substitution quite a lot easier. And we see it does. So what I'm looking at here is if I have that pyridine ring, and I'm going to just draw that to make it aromatic. What we have a question now is, where is the best place to put our chlorine? Do we want it meta, or do we want it ortho or para? And that's actually back to, it's better to say the 2 position, or the 3 position, or the 4 position. And we actually can make a call on that. If we look at our resonance contributors in there, if I actually attack the 2 position or the 4 position, I make a very stable species that has a pair of electrons or 2 lone electrons on a nitrogen with a negative. And that actually is quite stable because the heteroatom can handle that on there. So because of that, we actually find that the best place to put this chlorine to do nucleophilic substitution is in the 2 or the 4 position. And heck, I will do this. And I'm just going to say we're going to put in a bunch of OCH3 minus, maybe a little bit of heat. We will replace one of those chlorines, and I'll replace this one because it's a little bit less steric hindrance. And I don't know why I did that. We'll do nucleophilic substitution without too much difficulty as long as it's in that 2 or that 4 position. Now, speaking of having 2 groups on there, when there are 2 different groups on there, the best leaving group is what leaves. So on these 2, bromine's a better leaving group, so it leaves. Chlorine's a better leaving group, so it leaves. If it happened to be a chlorine and a chlorine, you will get mixtures, but this electron stability away from the nitrogen will typically help a little bit more, but it does need to be in that 2 and 4 position. All right, now side chain reactions here are very similar to just a regular old benzene. So the nitrogen or the heteroatom in general is not really affecting these. Excuse me. So if we treat the ring with MBS, it's going to put a halogen bromine right on the benzylic position. And if we treat a carbon that has at least a hydrogen off there with chromic acid, we will turn it into a carboxylic acid without any trouble. All right. Diazonium salts are a little bit different story there. So it's not really fair to say you can't form a diazonium salt. You just will only be to do one thing with any diazonium salt. So it will never actually exist as a diazonium salt. These will be very, very short life. And the reason that is because the sodium nitrite, and the HCl does indeed make a diazonium salt. But the water that's already in there will immediately react with it, and you will actually get an enol, which will automatically rearrange itself into a keto. And it's just because it's more stable that way. And it doesn't matter, there's nothing I can do to stop that. I can make the diazonium salt, but it'll immediately turn into an O. So, and that's what we would write. So if I wanted to turn that into the keto form, this is what I use. It's not really a 2-step reaction. This technically has the water in it. So it is going to get you that enol and favoring the keto. And while this might look like it's not aromatic, it actually kind of is, because this nitrogen has a lone pair on it. So does that one. And even though that's not giving a lone pair to the ring, it does have a p orbital. So I have a continuous ring of p orbitals, and I have 1, 2, 3 pairs of electrons. So it is actually aromatic, even looking like that. All right. Now, another weird thing that we have that we see on this deactivated ring with the nitrogen, a single methyl, and it has to be a methyl, a CH3, in that 2 or 4 position almost behave like they're an alpha carbon to a carbonyl. So we can actually have that react like an enolate ion. And because of that, because it can act like an enolate ion, we can just treat it with OH, create the enolate, and do an aldol condensation, where it will come in and attack the backside of that carbonyl. Or I can treat it, and it would be this one gets turned into, that's in the 2 position. And then this thing is going to, well, that creates the enolate. This guy is going to attack the back of that methyl, and we'll add a methyl onto that location. So everything that we saw with the enolatable positions will happen to that single methyl off that pyridine. All right. Last little weird class we're going to talk about and spend some time on is this amidazole. And all that we're really focusing on is this 5-member ring with the 2 nitrogens on it. Now, what makes this actually very interesting is when it's aromatic. So they're having it drawn like this, and the lone pair is on the inside. That amidazole is actually an aromatic ring, and it's a very common biological. Histidine is one of our amino acids, very common one, obviously. It actually has this amidazole ring in it. Now, something that makes this imidazole very, very, very unique among all these heteroatoms is it's acidic and basic. Obviously not simultaneously, but the two nitrogens behave totally different. Now, one of the nitrogens, its lone pair, is making up part of the aromatic cycle. The other nitrogens' rings are in the outside. So that location's still basic, yet this one will give up an H really well. So this has the best pKb, and this one over here has the best pKa. And it's such a big difference that we actually have diprotonated forms of it, and we have deprotonated, and they're both kind of stable. So we can add IHs to it very easily, we can remove them very easily. And it's actually kind of stable no matter what we do, because we're not losing the aromatic properties by adding the protons or removing them. They stay aromatic always. All right, but that does actually offer us an interesting reaction. So if we have imidazole and it's got a methyl on it, and we just put bromine iron bromide, where does it go? So we have 5-member ring, and I got one methyl. You notice how we got 2 nitrogens on here? I'm just going to arbitrarily decide that's one. All right, now when I put my double bonds in, that one's always double. The one that's across from this could have had a hydrogen if it was a regular imidazole, but it's got the lone pair here, so therefore this one's alone, and this has its lone pair over there. All right, so there is our 1-methyl imidazole, and we are going to react that with bromine and iron bromide. Now, if you think about it, back to what we were doing back in electrophilic aromatic substitution, we're putting that on one of these locations. Well, we have technically 3 different locations, here, here, or here, and we're going to check all of them, because there's is a slight bit of hindrance to be here and here because they're close to the methyl. That's not really strong enough. Methyl is not really that big. So I need to figure out, well, if I have it attack the 2 position. So let's look at what would happen if we attack the 2 position. So I have my nitrogen, have my methyl, and I'm going to say we're going to go on here for bromine and still have the hydrogen on it. Well, that would break this bond, and that would move the positive up here, and everything else would be exactly the same as it was. Now, I can move this down here and move that positive up. And can do that one more time. Guess that methyl's still there. And the positive is now here. And that's it. So I got 3 ways I can do that. So the C2 does accept it in 3 different locations. I can put a positive on that nitrogen. Yeah, I like that. 3 different contributors. Okay, so that was 2. We'd have 3 and then 4. So let's look at C4. And we're going to do the same thing. I'm going to change the ink color here. So I have nitrogen, but I'm adding it up here now. H and Br. This still has the methyl. Double bond was here, so that location becomes positive. This still is a double bond, that's still a lone pair. And I can move this here. Making that nitrogen positive. I can't really do anything else. Okay. One more possibility. That'll be C5. Which will put the positive here. That's still a double bond, that's still a lone pair. And then we will move this up here. That puts the positive down below. And I can do that with that particular location. Alright, so I got three contributors there. Alright, so it's definitely not C4 because C4 only gave us 2 contributors, and we have 3 contributors from C2 and C5. And if we look at these, we have a secondary, and we have the positive on a quaternary nitrogen. We have the same quaternary nitrogen, we have a secondary, so we just need to ask, is it better to have on a nitrogen that would be an incomplete quartet, because this just has one more pair on it and make it positive, or is it better to have it on a carbon with incomplete quartet and the carbon is better? So I would expect our major product then is going to be in that C5 position. Now what's interesting, when we have heteroatoms like this and hetero rings with multiple carbons, we don't try to say it's always the 2 position or whatnot. We kind of have to check stuff like this. And this is an interesting one where the C5 is going to leave us to a more stable intermediate, therefore that should give us our major product. The C2 is not going to be none, so you are going to have some where it's a bromine in that second location as well. It just won't be nearly as much. Now, where this gets to be a little bit more complex is these rings get slightly a lot more complex. Like even this, we might have a conjugated system made up of 2 rings that are bridged together. Now, for the most part, when our book looks at these, it's going to look at first how we might make them, and then maybe how we do electrophilic aromatic substitution to it. But this is a neat little reaction where we're actually starting with a benzene ring that has this diamine type thing attached to it, and then you're reacting with a ketone. Now, mechanism shows how this all goes, and it is actually kind of a neat little thing that you have to start with this guy, but it's what actually attacks here, and we make like an imine. And this imine has almost the perfect shape to allow this conjugated reaction to occur, and what's actually going to happen is you are going to break apart this bond and form one up here. Now everything else kind of moves, so it does look like some bonds are moving around. So you get a double bond there instead of here. But you do make this cool little thing. And now this NH2 is able to do a backside attack on this NH that forms that double bond. And that's what creates that second ring. And then since the acid will allow that to be a good leaving group, it does kick it off and we form a new double bond, giving us this indole. And it is a great way to make that. And the biggest reason Fisher wanted to know how to do that was because they're researching how to make things like purine, which is a building function for our amino acids and not amino acids, our DNA and RNA. Now, we will actually mostly do some very specialized fine reactions with it to try to figure out where's the best way to do little substitutions and such. But you kind of have to do any of those by drawing out all your possibilities to figure out where it's going to go. Fortunately, when they start to get big in biomolecules, we don't do that a lot because Mother Nature doesn't really. Mother Nature kind of has the game plan of what they all look like. Where this will come in handy a little bit later on is it will help us to see why One of those is found in DNA and one of those is found in RNA. Has a lot to do with the fact that it's a reversible reaction. All right, and last little thing, they start to go with some big rings, and this guy is made up of a bunch of those Pyro Rings, and just actually connected to one another. And we see it pop up in a couple key things. So it's the main central feature of hemoglobin, the heme group, and it's also found as the main contributing feature in chlorophyll. But common little things. But we will see some of these in our problems and such. But the electrophilic aromatic substitution really is the only part of this stuff that's new, and the nucleophilic substitution. But the rings and the aromatic rings with nitrogens and oxygens in them. Other than that, this is a review chapter for the most part. All right, thank you.